Alright, so I'm going to be talking about my mandatory 2. I'm not going to be going into details with the Pacman. It's all the same as the mandatory 1, so just refer to that if you need to with the wonder bias and simple phi and so on. So I'm going to be looking at the algorithm here, and the first thing we do is we create a node, which is the first node in the algorithm. We have some attributes. I just picked some that seemed relevant, and the same. I just created some examples. They're not optimal. They're just there for purposes. It works, but it's not very refined. And we put these into a list, and then we call the make tree, which is the main function, the recursive function that creates a tree, gives it the examples, the attributes, and the node we created. And in the make tree, the first thing we do is we compute the entropy of the examples that we get, and it's pretty simple. Let's see here. There we go. So if we only have one example, we return 0, 0 empty entropy, and then we go through the examples, and we simply create. We have this dictionary where we count up the all the different actions, and then how many examples have this action as their action. Once we have that, we can actually compute the entropy down here. So where we go through each different action and look at, well, how many examples had this action divided by the total example count, and then we compute the entropy from that number and return it. So this is the total entropy based on the for the first time all the examples. And once we have that, we go back here, and I create this attribute called final action, which is something I'm going to use when I'm actually implementing it in Pacman. So if the entropy is 0, we can just return. That's going to happen at some point because it's a recursive algorithm. So this is gonna happen again, recursive function. And then we actually go through. This is the main thing about the ID3 algorithm, where we perform these splits based on attributes, where we go into the split by attribute function, which we can see here. We create this dictionary, and then simply for each value that we can find of this attribute that we're currently looking at. So in my case, it's only going to be true or false, and then we just make a split based on that. So we have one list where all the examples have this attribute as true, and another one where all the examples have this attribute as false. And then we return this down here, and then we actually compute the entropy of these two sets. So how much information could we gain from this split, basically. And we subtract that from the initial entropy, and then the best result is the one that gets saved, which is down here, where we make the comparison for each attribute we check. So in the end, we have the test, the split attribute, which creates the least entropy. And so we make a new list of attributes, and we remove the one that we made the split on, because we're not going to be splitting on it again. And then at the end, we simply create the two daughter nodes. So in my case, it's only going to be two daughter nodes, but it could be more if we have more values. And then put these into the dictionary containing the daughter nodes that we can see here. Each node has this, and then we call the for each node we call the make tree again, and we give it these new attributes where the one we just split on is missing, and we give it the set, and then we just pass it the node that we just created, and then it keeps going. And so the things that I implemented is simply that I created this make decision function in the decision node, where we can call this, and then we say if it doesn't have a test attribute, then it was one of the leaf nodes, and we can just return the action. Otherwise, it still might have one itself, but then if it doesn't have a daughter node, which has this attribute value that we're giving it, then we're also returning the final action. But if it does have a daughter node, then of course this is also recursive. We just keep going down. And just to see at the end here, this is just where we create all these values based on the on the current state in Pac-Man. So we look, okay, is there a ghost close? Are there few pellets left? All these kind of things. So we continuously passing this to the tree that we just created, and it's going to give us back which state should we be in. So yes.